Thank you for your introduction. Now, in this whole discussion about quantum entanglement, so far, we have concentrated on various features of entanglement, and I may just make a few remarks at the outset before I go into the central topic of my today's talk, that we would have a group here in Calcutta working on these various aspects of foundations of quantum mechanics, and now they play with quantum information theoretic aspects, and many young research workers are involved. And there are a number of our works which have been put up posters. So as organizers, we have been giving very short talks, so it will be a very brief talk on my part and also another brief talk by Archad. So in this brief talk, I'll be just speaking a little bit about a curious little idea we have been exploring very recently, and that was about studying the application and the relevance of the uncertainty relation in the context of two qubit states. Now, in this whole discussion of quantum entanglement and its implications, historically, two qubit states have played a central role, as we have extensively discussed in this conference also. And the motivation underlying the present work is to uncover any earlier unexplored features that may be revealed by using the uncertainty relation for the two qubit states. And of course, some studies to this end have been already done, and a number of Indian leading researchers have been also involved in this direction. And that's from the point of view of giving a number of different criteria for discerning whether a given two qubit state is entangled or separable. But the question we are trying to pose is that whether it is also possible to have a testable measure of the mixedness of a two qubit state, irrespective of whether it is entangled or separable. So that is the question we have been trying to study, and this question is interesting because if you prepare a two qubit state, then due to its interaction with the environment and so on, the coherence is lost. So the study of the mixedness of two qubit state, it should be an interesting question in itself. And then we try to relate this question to the question whether in this context a suitable form of the generalized uncertainty relation could be useful. So that is the motivation. And so to this end, we reformulate the generalized uncertainty relation, as you all may be knowing that the usual uncertainty relation know the Heisenberg form that was generalized by Robertson followed by Schrödinger, and that is known as the Robertson-Schrödinger generalized uncertainty relation, and that is what we reformulate. I'll come to the details in a minute, as something like a quantity z, which I will soon define, z greater than equal to 0 in this form, whether the crucial feature is that this quantity z involves mean values and variances of observables which are in terms of joint observables, namely the tensor product of spin components of two qubit states. So that is the crucial feature, writing the generalized uncertainty principle using the variables a and b in that form, in some special form. And then we calculate the values of z for a class of two qubit states, and we find that for any pure two qubit state, this generalized uncertainty relation is satisfied as an equality. And for the class of mixed two qubit states, we consider the choice of observables involved in defining the quantity z can be made such that this generalized uncertainty relation is satisfied as an inequality where the magnitude of violation of the inequality gives the measure of the mixedness. Now, as we all know, that the measure of mixedness of the quantum state, or to put it in other words, the purity of a quantum state P, if one defines, is given by the quantity trace of rho square, and we all know this property, that trace of rho square is equal to 1 for a pure quantum state, and for a mixed state P less than 1. But if you come to two qubit state, the minimum value of P is 1/4, that is for the maximally mixed states. And then the standard theoretical measure of mixedness is defined in terms of the departure of the value of P from 1 given by linear entropy for the two qubit state, and that is defined in this way, so that linear entropy lies between 0 and 1, 0 for pure state and 1 for maximally mixed state. However, linear entropy is not an observable quantity, and so the need for having a testable measure of the mixedness of a 2-qubit state, which would be consistent with the theoretical measure of mixedness in terms of linear entropy. And for this purpose, the generalized uncertainty relations could be useful. That is our observation. Now, what is the form of the generalized uncertainty relation we use? This is the standard Schrödinger-Robertson form, or Robertson-Schrödinger form, whatever you may call it. Historically, Robertson did it earlier and Schrödinger came later. And where not only the commutator is involved, but also the anti-commutator is involved. So it is for any two dynamical variables A and B, and this GUR, this generalized uncertainty relation, is written in this form, and we focus on this quantity on the left-hand side and compute this quantity for the classes of 2-qubit states we consider. Now, but before that, one of the crucial steps is to identify the observables A and B that are going to be used in writing that uncertainty relation. So, the A and B are the joint observables, the product of the spin components along the directions, and this choice of the directions is important. And that defines the choice of the observables A and B. And we take these directions M and P and Q to be all in a two-dimensional plane, with respect to which it is all taken to be coplanar, with respect to which the orientations of measurements of the Pauli spin operators on each of the particles are specified. And it is for the calculation and convenience and so on. So these directions are quantified by these three parameters, theta 1, theta 2, theta 3, where one of the directions is fixed along the y-axis and the other directions are accordingly fixed. So it is by varying these three parameters, you vary the choices of the observables A and B that are used in writing the generalized uncertainty relation for the 2-qubit state in defining or understanding the mixedness property. Okay. So what are the properties that can be shown and that can be shown analytically exactly, if one can just compute, is that first property, interesting property, is that for any pure 2-qubit state, it is satisfied as an equality. And as I will just display for by this, any pure 2-qubit state, one can have what type of pure 2-qubit states I shall soon display, but first let me give the general statements of the properties. For any pure 2-qubit state, this is satisfied as an equality, and this holds good when I say for arbitrary choices of theta 1, theta 2, theta 3, one means for arbitrary choices of the observables A and B. So that means the GUR in the form we write is always satisfied as an equality for the pure 2-qubit state. And for any one parameter 2-qubit mixed state, a range of, in fact a wide range of choices of theta 1, theta 2, theta 3, that is for a large class of choices of observables, one finds that the inequality is, that is Z is greater than 0. And what is important is that for this range of values of choices of the observables, it is found that if the mixedness of the state is characterized by the parameter P, the functional dependence of this quantity Z with respect to the mixedness parameter P is of a form similar to that of linear entropy with respect to P, and for certain choices of those observables, it is exactly equal to the linear entropy, and this can be called as optimal mixedness witness operators. So in analogy with what has been discussed as in the literature on entanglement witness operators, here we call them to be mixedness witness operators, and these are can be called to be the optimal mixedness witness operators. And when we say any 2-qubit pure state, it can be any 2-qubit pure product state, which can be of this form, any pure 2-qubit entangled state, which can be of this form or this form, where alpha and beta can be complex quantities. And for them, it can be shown that this for all arbitrary, for any choice of theta 1, theta 2, theta 3, exactly it is equal to 0. This is an analytical result. And also, one can demonstrate the interesting property. So this is for the pure state, pure 2-qubit state. Now, the very well-known and widely studied 2-qubit mixed state is the 2-qubit Werner state, which is of quite significance in the quantum information theory study. The Werner state is given by this, which is a mixture of 4 Bell-basis states as a singlet state, and noise, which is represented by this identity matrix, which is a linear combination of 4 Bell-basis states of equal weightage, and there is a mixedness parameter P, and this type of mixed state, this type of 2-qubit state has this interesting property that this mixedness parameter P between the 0 and 1/3, this can be always written in a separable form, that is in this form, whereas in this range it can be written it is in the entangled form under this condition in that range. And what is important is that for this Werner state, the linear entropy is given by this expression. Now what happens if we study, we apply the GUR in the form we have written for this class of 2-qubit states, then again a wide range of values of θ1, θ2, θ3 can be found for which this Z quantity is greater than 0, and the functional dependence of Z with respect to the parameter P is given by this quantity. So it is of a similar form as the linear entropy functional dependence on the parameter P, where A and B are functions of θ1, θ2, θ3, and for some special choices of θ1, θ2, θ3, one can make A and B to be unity so that it reduces to be equal to the linear entropy. So that is the point that I emphasize here, that one can find a subset of values of θ1, θ2, θ3 for which this equality holds good. And these are some particular examples, and these are the specific choices of the mixedness witness operators, the product of the Pauli spin observables. So the important observation is that writing generalized uncertainty relation in terms of these observables, one can get a relation in terms of observable quantities, which gives you a measure of the mixedness of the state. So just, and also then we have, when we are in the process of extending this study to other types of mixed 2-qubit states, but just to compare now this scheme with the approach using entanglement witness operator. How much time do I have?
7 minutes.
7 minutes, okay. So I think, so I'm not going into the further details of the other types of studies we have done regarding the other classes of mixed entangled states, for the mixed 2-qubit states. But here I just, the fundamental point, why this scheme should be interesting enough to study. Let us compare this scheme with the approach using entanglement witness operator. What happens in the entanglement witness operator approach? Suppose you are given an entangled state, then the corresponding, there is a prescription for defining the entanglement witness operator, which is Hermitian, and for which the trace of this quantity is always negative, that is the expectation value of this entanglement witness operator is negative for the given entangled state, and for any separable state it is positive and greater than equal to 0. But it's important to emphasize that if you are given an arbitrary state, arbitrary unknown state rho 0 for example, then if this quantity is greater than equal to 0, the state can either be entangled or separable. So being negative is enough to say that it is entangled, but greater than equal to 0, if you find, if I construct an entanglement witness operator, you cannot be sure that it is entangled or separable. It is only if it is negative you can say that with certainty that it corresponds to an entangled state. On the other hand, in using our approach in terms of mixedness witness operator, for at least for a class of 2-qubit states we have studied so far, it is possible to discern with certainty whether the state rho 0 is pure or mixed. Now let me explain this statement a bit within a couple of minutes. What I mean by that is that suppose I determine the quantity Z for a given unknown 2-qubit state in terms of the mixedness witness operator, and we get the quantity Z to be not equal to 0, then we can be certain that the state in question is mixed. But suppose one gets the quantity Z to be equal to 0, that is the GUR is satisfied as an equality, then that state can either be pure or mixed. But one can draw further inference by redetermining this quantity, by measuring the mixedness witness operators, by just changing the settings of the observables alpha and beta weight. For example, it suffices to vary at least one of the theta's, that parameter, at least the choice of that observable by, say, of the order of 0.1 radian. Then if one still gets 0, then one can be certain that it is a pure state. The point is that for a very wide range of values of the choices of the observables, those properties hold good. For even if for a particular choice it is you find that it is 0, then if you vary the choice of the observables by even a small amount, and you can check again whether it still remains 0. If it still remains 0, then the state is definitely a pure state. Otherwise, the state is a mixed state, and even if you change by, say, 0.1 radian, the Z changes by this value. So experimentally, it is possible by varying the choice of the settings, one can determine whether the given 2-qubit state is pure or mixed. And of course, with the increase in accuracy of the measurement of the observables involved in defining the quantity Z, even for a smaller variation of one of the theta's, that is for the choice of the observables involved in the GUR, the departure from the equality of GUR for a mixed state can be discerned. So in this way, one can be, for an unknown state, for an unknown 2-qubit state, one can find out whether it is pure or mixed. But so far we have studied only one parameter class of 2-qubit mixed states. So our approach needs to be applied for a wider class of 2-qubit mixed states involving more than one mixedness parameter. For example, one has to consider the so-called Bell diagonal states. And another interesting direction of study could be that what relevance or significance the scheme suggested in this paper could be useful in the context of studying the decoherence models, because given an unknown state, the decoherence model is decoherent. So I suppose an unknown state you prepare, you are more or less sure that it should be pure, but then after a certain time you find out to what extent it has become mixed. So whether this can be useful in studying some features of the decoherence model. And finally, note that this feature we find that this GUR given is satisfied as an equality for any 2-qubit pure state, whether it can have some deeper implication or significance. Thank you.
Taking measurements, simple expectation values. But if you have 2 copies of the state, then you can